code is available, we have to follow that code. So that is why I specify the study hypothesis, and whenever you go for the study hypothesis, you have to develop an overall study protocol. So choose or prepare that the specific instruments, and also once somebody is trained for quality control of the data, then he should always consider the further train of the trainer. That means you have to give the certification that these are the people who can maintain the data quality. Okay, so they have to develop the operational manuals, they have to develop the technical specification for the data quality to be maintained. So then we have to have a quality assurance. Why standards important? And preparation of the written manual of operation, because once that the data quality for a particular job is assured, then definitely you cannot change. So therefore you have to have a protocol and you have to produce that technical report. So trainings of the staff is very, very important. Here our basic aim is to make each staff person thoroughly familiar with the procedures under his or her responsibility, so that whenever he will be in the round the clock shift, so he should be independent. He should not disturb the other people that why the data is coming. Mostly if you go to the plant, water quality plant or any other plant, thermal power plant, you will see that the shift charge engineer sitting in the control room. So they understand that what kind of data quality is coming, because based on the quality of the data, they have to take the decision for running the plant. So operational part of a plant is based on the quality control of the data. If any aggravations occurs, then definitely they have to take the shutdown for operating that plant. So they have to shut down the plant. So these are the pre-testing and pilot testing for the data should be taken care. And when you will do for that, you have to go for as a data management procedure, designing your data collection. That means you have to make a flowchart where from the data is coming and what kind of data is coming. If you have removed the noise, what are the method you have followed? If there is an error, how that the error can be analyzed. All these things should be properly written in the manual. Okay, so now here you see when you are entering the data, we use the professional data entry program like AP Data. So this is a software. You can download the software where you can enter the data by using that. And remember that whenever you enter a data, you have to always, a very simple protocol is that you have to always check a duplication prevention. So duplicate entry of the data prevention is basically done by the binary search method. So that technique should be adopted while entering the data. So that means in the AP Data, this software is embedded. So then you have to preparations, as I mentioned, that the complete code book, and then different questions are there. And this kind of book should be available at the station from where the data is taken and managing. So if now you see that if there are error, how to do that? If errors are discovered, then you have to always go for the error analysis. That means whether the data is coming in the 3 sigma level or it is coming in the 2 sigma level, that we have to decide first, and then based on that we have to take the decision. So if errors are discovered, then when comparing the files after double data entry, as I was mentioning that you have to take care, because sometimes if the duplicate data entry is not prevented, then there may be a large amount of error flowed into the data. Okay, so you have to split the process into the distinct and well-defined steps, and then also whenever this occurs, you have to basically provide an archive. So this documentation is always available in any standard textbook, not textbook, in standard code book for maintaining the data. If you go for the data quality control in the international platform, protocols are there. So one has to follow that protocol only. Okay, now assuming that you have got the lot of data and the quality control you have followed, so the data is error free, noise free. With that data, you wanted to do some kind of model, and data driven model, it is always good, is always better than any deterministic model, because it talks about the data, so that whenever the data changes, if the data changes with respect to the time, so model also behave accordingly. So therefore, data-driven model is always, we can say that the dynamic model, or it is based on the time. So as we proceed towards the different time, so my model also will be changing. So that is the beauty of the data-driven model. And there is no assumptions or postulates provided in the data-driven model, assuming that the data is normally distributed. Or if it is not, then people try to make is a normal distribution by maintaining the quality. So simple linear regression is also a one kind of data-driven model. Here, basically, what we do, we fit a model, and that is always checks for inadequacies. So therefore, we require a minimum statistical knowledge for developing this data analysis, developing this kind of model. What is the method we follow? We follow the least square error method. So as a minimum, the residual should be plotted again. And when you do that, you have to justify by plotting. So therefore here, we try to plot the residuals that should be plotted against the predicted values of the fitted model. And then based on that, we can compare what to do there. There is a quantification also, how good your fit is. So now you see that I have this plot, as yesterday I was telling that when you have the scatter plot, I can fit a simple linear line. And if you look at this line, then you will see that some of the points are above the line, some of the points are on the line, some of the points are below the line. So that means I have drawn a line, rather the model has generated a line, which is my model, and which is gone towards the maintaining the error as a minimum. That's all. So this is my xn plus 1, and this is the corresponding yn plus 1, and from there we developed a model. And whenever we are predicting a model that is estimated, so the cap is there. So cap indicates that it is a estimated model or developed model. So this model is simply a W0 plus W1 xy. So we can always mention if there is some more other variable like xi1 and xi2. So therefore, data-driven model is nothing but a model which is prepared from the data as a following the linear regression or sometimes non-linear regression. Okay. So here, whenever you have, so you should produce the data always in the matrix form. So therefore, this particular thing we write in a matrix form, which is the X transpose and corresponding the weights. Okay. So suppose that now let us example give the with respect to some data. So I have my data points which I have mentioned as a x1 y1 x up to xn yn. That means n number of data we have. So I can develop a model y equal to function of x, which is beta 1 plus beta 2 x showing here. So our idea is to generate a model. So that means that beta 1 and beta 2 I have to estimate it from the data set. Okay. So we apply the ordinary least square method, and as you mentioned that as I told that the ordinary least square method, this is my residual error. That means this point is not on the line, there is slightly above. So how much of residual? This residual, more you have the minimum, so you will have the better fit. Okay. So therefore, in just as a diversion, people always try to do a machine learning technique here. So they wanted to know that how many data points are on the line and how many data points are below the line or above the line. So they wanted to classify the data before fitting, and that type of technique is known as the support vector machine or support vector regression. So some other time, if you talk about only the machine learning technique, so this is another technique for developing a data-driven model, which is far better compared to the only ordinary least square method. Whatever it is, so we have the technique that the sum square error, and this particular thing we have to minimize. That means we have to take the derivative with respect to the weights, whatever you are asking. If you do that with respect to the error, I'm not going to the detail of the maths, is already covered, hoping. So this is my sum squared error denoted by E. So that E is a function of the weights. So I have to differentiate with respect to the weights. If I do that and make equal to 0, because the first derivative should be equal to 0. So you will get this kind of matrix equation, which is a linear equation. And then finally, this equation we can convert into a simple matrix form. This I have shown you as a matrix, and this is my weights, which I have tried to calculate, and this is my augmented vector, so B. So therefore, I have a system AW equal to B. So W can be calculated by taking the inverse of A multiplied with the B. Okay. So therefore, when you have that, so you have to know that really whether you have minimized the error or not. So to do that, so this is the formulation we have shown. So then we have to go for the actual linear equation. So now if you look at the methodologically, as we know from our very old syllabus, that for the y equal to beta 0 or beta 1 plus beta 2, we can just simply write a normal equations, and then we can apply the Gauss elimination algorithm or determinant method, analytical method. So beta 2 and beta 1 can be established into that form. So many of the time, if these variables are long, you may not be having any your complete regular equation, because some of the data may not be available or the determinant may be singular. So therefore, remember, in that case, if we write the whole equation in the form of a matrix, and if I find it out that inverse of the matrix does not exist, then there are a method called singular value decomposition. So the singular value decomposition is a technique which we have to apply whenever such kind of irregularity in the matrix is available. Okay, for the time being, we are not going to that complications. So now let us see that data set. This is my x data, this is the y data, and remember y is the response of the dx. So I have simply plotted the scatter plot, and then we try to find it out. The whatever the equations in the previous slide I showed, the same thing, all these components I have calculated with this data. So sum of the x, sum of y, sum of xy, and sum of x square, you can simply calculate. You calculate also average x, average y, average xy, then beta 1 with respect to that formula, we can easily find it out, and beta 2, that the denominator numerator is there. If you look at this expression, so this is the numerator, this is the denominator for the beta 2, similarly for beta 1. So therefore, if we do that, you have this fitted model which I am flashing here, y equal to 24.45, 0.509 into x. So with respect to this data given to me, we can follow the least square error method as an ordinary least square method. So we can calculate my weighted coefficients. That's all. So finally, you have this regression line into this form. Y equal to beta 1 is your constant, that is intercept, and this is your slope. So this particular thing, when you, because as I mentioned that if x is more, that is x1, x2 actually huge, then the normal equations development will be that many parameters. So you may not be having proper solution. So we have to convert into a matrix form. If we convert into a matrix form by using the matrix method of operation, you can simply write that the beta as a x transpose x inverse multiplied by x transpose y. This is very healthy. You see that compared to the previous expression, here it is a very healthy, because I know that the x as a vector, so I can easily transpose, I can calculate the matrix, and then as I mentioned that if this inverse does not exist, or if the inverse having some problem, then you have to apply the singular value decomposition into this domain and then proceed. And singular value decomposition, I know that the people already have encountered with the maths class in the first year engineering or second year engineering. So then you multiply by x transpose y, so you will get the beta value. So this expression generally one should apply in a, when Anindita will show that there is some exercise in R, so she should do an exercise for how to calculate the beta. So finally, the beta can be written into this form, and this has got the meaning, as I mentioned, that this particular component is a diagonal matrix with 1, and the variance of x is the diagonal. Okay, so therefore, this matrix, if I use, I can easily find it out what should be my constant value, and then model can be developed. So interpreting the beta 1 and beta 2, beta 1 is basically is the average of the y. Whereas beta 2, if you look at, it is a covariance of x and y divided by the variance of x. So that means if there is no covariance, and once that the covariance exists, you can always expect there is a correlation exists. So if x and y are not covariant, or if x and y are not correlated, then definitely you do not have any beta 2. In that case, only our model is a constant, which is a response average. That's all. So the interpretation of beta 1 and beta 2 is nothing but that beta 1 is my constant because it is the average value, and beta 2 is a covariance, and in the form of a matrix is a covariance variance covariance matrix. So therefore, I have this equation in the matrix form, that error is minimized. So now you can see that the beta 1, beta 2 we have done. So we can beta 2. So automatically, if you do the matrix method, of calculation, you have the y, and then you try that beta 1 is equal to y bar minus beta 2 x bar, and beta 2 is equal. So if you have x and y, having this assumption that it is a linear regression, you can easily calculate covariance y, you can calculate so beta 2 you can directly calculate. Once you calculate beta 2, these components are already coming from the data, so you substitute the value of beta 2, you will get the beta 1. So this is very simple, and you check that whether it is a minimum or not. Automatically, if I do the minimum, so you will get the beta 1. So that means minimization of the error is generating this expression of the beta in the matrix form. So always we should write a program for computing this formulation for getting the beta, which is my coefficient. And then, as I mentioned that after fitting that, you have to understand that what is my goodness of fit statistic. So that is done by the capital R square, which we call in the index of determination, and which is done by if you look at that, it is nothing but the variance of the model and variance of the data given. So if the variance of the model and variance of the data given almost same, so R square is coming as a 1. So the more R square towards the 1, my fit is best. So therefore, R square statistic is the ratio of the variance, as I mentioned. So therefore, depending on the R square value closer to the 1 will give me the decision that my fit is the best. Okay. So this is here you see again that I have a hydrocarbon data x and y. I can multiply the x plus. I can do this one and then x. So y fit model I got that. So now if you see that my y value data is 90.01 and here it is 89. So there is a minimum error. So if you do that, the R square calculate for that. So this is my y fit model. The value beta 1 and beta 2 I have shown here. So my model is giving here. So based on that, and then we can always calculate the R square value and y fit square, because R square I am trying to calculate the residual square. So if you do that, then you can always calculate this ANOVA table. In the ANOVA table, you go for the degree of freedom, residual error for n-2, for the total is n-1, and these are the components of the ANOVA table. Sum of the square of the residual, sum of the square of the error, sum of the square of the total, and then you calculate the mean square variance by using this formulation, and then you also calculate F statistics. And if you see that the table value of F statistics for this degree of freedom and for the certain level of significance, if it is less than the table value, then your model is accepted, and always you will get from the what is the significance level, that is p value for your fitness. Same thing we can apply for the multiple regression. That means some more variable will be there, and if you do that, you know that already we have expand. So the x prime x by n, it is a variance covariance matrix, which is very, very important. And in many process, variance covariance matrix development is very important. And this you will not get if the data is noisy. And that is the justification that the data should be noise free, data should be error free. Okay. So these are the problem I'm showing here. I have a data pool strength, wire length, die height, pool strength, and so ultimately y is a fitting with the x1 and x2. So I have given shown because there are huge number of data. So ultimately I am trying to fit my model as a beta 0, beta 1 x1 and beta 2 x2. So if I do that, the same procedure, I have the x matrix, I can apply x prime x, so it will be x prime x. I can calculate x prime y. So this formulation I applied and then got the value of at a single stroke, you will get the value. So my model is now, this is beta 0 and this is my beta 1 and this is a beta 2. So my model is ready. So this is the basic story of the data-driven model. If the data is spatial data or if the data is time-related data, then also this method can be applied, but there are certain steps which I'll be talking about. So now after doing that, you have to calculate the variance, which is sum of the square of the error divided by degree of freedom. And this formulation I have shown. So if I calculate, I will get this figure, which is now 5.2352. Variance covariance matrix, you can calculate. And then by using this formulation, variance covariance. Now you see that for every parameter, your 95% confidence level is this much. For beta 1, it is this, and beta 2. That means your parameter estimation should follow within this at a 95% confidence level. If you find it out, some data, somebody is cooking and try to fit a best line and find it out that beta 0 is going beyond this or it is low, that means you can reject. So there only you can check that your data is really proper or not, or if somebody has presented or not. Okay, so now you see that sum of the square of the error I can calculate, sum of the square of the residual error, sum of the square of the error, and if I do that, then again as I mentioned that you go for the ANOVA table, generated the F statistics and get the p value as I mentioned that here. So therefore you understand at this stage that a regression model can be applied as a data driven technique. Okay, assuming that data is normally distributed. This is remember, okay, because if the data is not normally distributed, suppose some data are log normally distributed, then you have to transform the data by using the Box-Cox transformation. So if you, so therefore if you try to, how do I know that my data is a basically normally distributed or not normally distributed? That is done by doing some box plot, which I will be showing that. So box plot is the first checking that where you have to proceed for developing a data-driven model, either by normally distributed data or by non-normal distribution. So therefore, now let us go to a technique called exploratory data analysis, because when you go for the data analysis, there are two techniques. One is the data envelopment analysis, that is DEA, or another is the EDA. EDA is the exploratory data analysis. That means we are explored the data. So all sorts of possibilities of data we are trying to analyze. And then after the main analysis, I have to visualize. Until and unless I visualize, I may not be in a picture there, because many people do not know that the math, so they may not be interested. So, but if I pictorially show them that this is my analysis, they will appreciate. So anyway, exploratory data analysis, visualization, very important steps. You know that they go to your node data. That's why I mentioned that you distributions, symmetric, normal, skewed. You have a data quality problems. You have to do that the outlier. So many of the times you have to remove the outliers, but sometimes removing outliers is a very crucial and judiciously you have to remove. You have to go for the correlations and so on. So sometimes EDA, we have to, our goal, we have to analyze that. So in the exploratory goal analysis, the goal is that they get a general sense of the data. As I mentioned that you go for the various techniques, quantiles and box plots. I was mentioning that the box plot because by using the box plot, you can easily find it out where your data is quality. Okay, whether it is a not quality or you have to do something. So here the data driven is always a model free. So because of this, I can always take a challenge. My data driven model is always good. When I talk about model free, model is always based on certain assumptions or postulates. So that is why, but here it is coming from the data only. That model is coming from the data. So therefore, there is no model adopted in the data. So therefore, data driven model is always better than any kind of model which has come from the postulate. So interactive and visual things can be done and especially useful. But here at the point, I wanted to mention that the data which I showed, that is a continuous data. But suppose if somebody gives my X value is running from 20 to 30 and Y value is running from 50 to 55. With this information, how do I proceed towards the data-driven model? This is a challenging thing, and there only a Anindita can take a R program to understand that if the data is ranged, input data as well as output data, how do I apply my regression technique? That exercise today night session she can show. So as a summary statistics, we already have to know, and as everybody knows from yesterday, Dr. Kaushik's lecture, that what is the variance, skewness, quartiles, everything can be calculated with respect to the model, and then find it out that what is the statistics to be adopted. Okay. So visualization as far as concerned, you have to go for the histogram. Basically, we are satisfied always with the histogram because frequency directly we cannot plot, but histogram we can plot. Okay. So issues, there are some histograms issues will be there that we have to take care whenever we handling the data. Fine. So these are yeah, I'm showing where the histogram, because you see after the histogram, if you try to fit, so some of the informations you are excluding. Here also some of the excluding. and here again some more, and some more unwanted information you're adding. So whenever you try to plot a histogram, and if you give your report in a fitted curve, so be careful about that, because you may be inviting some unwanted information which was not there in the data, or you may have deleted the wanted information which you require. So therefore, so what you have to do, we have to apply a histogram technique by a method called kernel smoothening technique. Okay. So in MATLAB, if you go, you have a KS density that is called kernel smoothening density. So here I am talking about the kernel estimate for smoothening the data before the or this one. Now I have to apply this technique, which is a coming from the kernel smoothening technique, and this kernel can be a Gaussian kernel, this kernel can be anything. So kernel smoothing technique will allow you to choose your kernel, and if you do that, you see that you have optimally smooth, because many of the times if you have a spectral data or many of the frequencies, then actually having a baseline for restoration is very, very difficult. So in that case, we always go for a kernel smoothing technique to get the actual fitting. So here I am showing that it is an optimal method. Same way, you can go for the bandwidth, because you see here so many jittering is there. So if I try to smooth by kernel smoothing, I will get that. And the best part is that the kernel smoothing, if you have a low data, and means less number of data, you do not know that whether it is normally distributed or not. But if you run the kernel smoothing, it will give you the knowledge that is it a normal distribution or not. Most of the time, kernel smoothing, it measured data, it converts into a normal distribution with no error. Okay. So therefore, as I was mentioning, that this is one part of the quality control of the data, because simple data, I apply the box plot. If I do the box plot, I am showing the box plot. This particular line, if it is normally distributed, it will exactly divide this zone into two equal halves. That means my mean, median, and mode all are lying on the central zone. So if it is so, then automatically my data will be normally distributed. And this is giving your 75th percentile, and this particular age is giving your 25th percentile, and this particular is giving your minimum, and this particular line is maximum. Any data below this is called as the outlier, and any data below this is known as the below detection limit. So if you have the many more below detection limit, then you have to improve your instrument, or instruments may be faulty, or your measured location may not be proper. So this concept you will get by using the single box plot, and then you are maintaining the data quality. So that is the beauty of the box plot. So once you have the data, first you plot the box plot and find it out what is my data, whether the quality data or some problems is there. So then when you apply this thing, if you plot a data into this form, it is a temporal component, you have this kind of jittering. So here you see that the summer peaks, that summer bifurcations for air travel. So basically with respect to the time when you try to plot this kind of sequence, when you have a simple time series data. So time series mean versus weight. If you take, you may have this one. And when you have this kind of thing, you can expect a linear regression, because some trend is showing. So that is why trend analysis is very important in case of a time series, because trend, it will give me whether I am in a position to plot the data in a regression format or not. So that is why in the time series we have some mere components, trend component, seasonal component, irregular component. And so therefore our basic aim is that whenever you go for a time series data driven model, we have to decompose. So after the decomposition, trend part we can always follow by a linear regression. Seasonal, we can follow some other. So therefore, irregular, it is a random walk, we can apply the random walk technique. So there are many more techniques are there in that. So this is basically to show that how the data series means time series data driven model can be developed. Okay, so these unexpected patterns, you can see that some of the steps are not proper, so some possible explanations we have to interpret. So therefore, if we look at the spatial data, for example, if your data has a geographic component, you can exploit it. See, everywhere I am forcing you to understand that you should always plot the scattered plot. So these are earthquakes in Pacific Ocean. So data from the different side. So can plot as always a scatter plot. Do not join the plot. So every time if you plot the scalar plot, you can understand that what the data type. Here by this plot I can understand I have this particular domain. I have that means there is a mixture of two events. So I can easily find it out by using the technique called cluster analysis technique. I can find out this is one of the epicenter of the earthquake and there may be one of the epicenter of the earthquake. So earthquake must have occurred at the two places subsequently at the different time or the different locations. So that kind of interpretation we can find it out. Okay. Here you see that the scattered plot. Now, if you give the plot, and if I ask you a data quality control man, that can you find it out how much of data is there, whether the data is single data resource coming from the single resource or data has come from the many more resources. So therefore, those kind of things to find it out, we require to do the cluster analysis. So that plus these are the machine learning techniques. So therefore, machine learning technique or simple statistical, advanced statistical method is applicable to understand the data quality, which is sometimes we call the data fusion method or combinatorics. So this is a scatter plot, is a single data. So just a linear relationship. And then this is a quadratic relationship. Now I am showing you that everywhere that the scatter plot is must, and then you fit a line through that. And then you'll come to know how good your fit is. To do that, we have a better method, as I mentioned, the support vector regression. Yeah, that's the machine learning technique. So then again, if you have a plot, it is a homoelasticity. So you can see that all your data is falling within a band. So whenever you have a band, that means that band is important. So I can give the range that my data is running from at x is equal to 40, my data set will be that. So that's why I told that Anindita can show that today in the night session that if the data is range, input data, output data, how to do the linear regression model is a very important domain. So then again, if it is a heteroelasticity, you can see that how the data changes take place. So therefore, the understanding by scatter plot, homoelasticity and heterogeneity can be easily known. Similarly, if we have a huge data like that, so it is a very different to understand that how much of data is there. So there are two variables which are continuous. When there are two variables, overlapping data, sometimes if you remove as an outlier, then neither you have this information nor you have this. So that is a judicially one has to take. You have a contour plot. So from the contour plot also, we can find it out whether my data is properly. So some of the contour I can choose. So therefore, idea is that when you have a bulk amount of data, we have to apply the dimension reduction, and this dimension reduction can be done by the variable selection, stepwise, and principal components and multidimensional scaling. So each and everything are very important from the data-driven model. Okay. So when you go for this kind of thing, so far we were doing the data analysis. Now, when you try to do this type of thing like quality control, you are assuring, you are reducing your dimension reduction. At the same time, you are judging your assessment. So all this type of thing is called as a data analytics. So this is the difference between data analysis and data analytics. Okay. So in analytics, we try to discover the pattern of the data by taking some decision-making procedure. So therefore, analytics is an encompassing and multidimensional field which requires mathematics, statistics, predictive modeling, machine learning. So when you apply the machine learning technique with the data analysis, we know as it is a data analytics. Today's domain is a data analytics. That is why simple statistics method is not at all applicable. One has to know that the computer science, lot of algorithm and lot of machine learning techniques like artificial neural network, deep learning, Kalman filter. So tomorrow's session, Kalman filter, I will talk about that. So with respect to the data analysis and data analytics from the computational techniques for data-driven model, we just try to show that the water quality monitoring. This is a full-fledged study. Here, basically, our objective is that the water quality index, as you know, it is defined as a sum of the several weighted indicators and regarded as a numerical measure of water quality. And as you know, that water quality is a time series data because you have a pump, you are pumping the water, and feeding to the proper station. There the water dosing is there, and then you are getting your water at your doorstep with a good quality. Assuming if the water is deteriorated due to some kind of dosing and all these things, then your health problem will be there. So monitoring water quality temporally is very, very important domain. So therefore two scientific methods are attempted. We have to know that the one is the decision making, as I was mentioning, which is a machine learning technique. There we try to do that this kind of multi-criteria decision making, because some of the data is a cooked data, or some of the data is not possible because of your low graded instrumentation adopted in the pump. So therefore, we require the time series analysis, which is a statistical analysis. And today we will try to explore some kind. And as you see that yesterday I showed you the Hertz exponent, there is a lot of techniques available, Lyapunov exponent, permutation entropy. So all these are techniques are very, very important domain. And I have hardly seen that the people are adopting this technique. I applied this technique for the Carnot state. Now they are free. So statistics required for this normal probability theory, correlation regression, logistic regression, maximum likelihood. Yesterday I covered that. Bayesian statistics, I will touch upon that. Apart from that, we have a LDA, that is linear discriminant analysis, principal component, system identification, which is done by tomorrow by Kalman filter, then time series analysis. And in addition to that, we have a decision making process, multi-attribute decision making. And I would like to request that the Professor Madhumita Dasarkar madam to have a complete FDB on multi-attribute decision making, multi-criteria decision making with an optimization technique, because people will be knowing that here what optimization technique. This is applicable for instrumentation as well as for any other field. And then finally we have a Markov chain Monte Carlo, which is very, very important technique. So water quality, I am not going to the detail. So we have a water distribution network, which is acting as a complex reactor system, and a lot of sensors are there. From the sensors, we are getting the data, and the data will be categorized as a physical, chemical, and biological contaminants. So now we need the data for allocation, engineering design, prediction, forecasting, and so on. So monitoring is needed because water is not distributed even in space and time. So, and water quality is to be maintained properly, otherwise health problem will be there. So from the healthcare, we have to know. Now water is coming from the pipeline. So the data quality has to be checked here itself, that whether all the pipelines are proper or not. That means right from the structure, right from its orientation, everything we have to check. Then in the water industry is applicable for agricultural, mining, forestry, hydropower, waste management. So therefore, it is always essential to the health and well-being for both public and environment. So that is why water industry is very, very important. Okay. So water industry. So therefore, extreme weather is going to develop. So therefore, this is the problem. And now you see, water quality failures is, so therefore, if there is a failure in the water quality, you may have some problem. So let us see that a realistic study. This is the Karnataka state, which has got some 27 districts. Each and every district, they have given a data to me, and from every district, almost 9 parameters they have given. So you have a huge amount of data, and these 9 parameters for each district they have collected for a period of 12 years. And daily average, hourly average. So it is a huge data. So basically you are handling a big data. So these are the districts as I showed here, Bagalkot, Bangalore, rural, all these districts are there. And their problem is that many of the area, people are calling some kind of dental problem, people are having some kind of different healthcare problem. So they wanted to monitor the water quality. So water quality data is exhibit the different kind of distribution, non-normal distribution. It has got a lot of outliers. That means a lot of missing values, and it has got the values of below detection limits and serial dependency. So therefore, generally people apply the normal statistics, but normal statistics may not be applicable much, because that is the difference between a statistician and a machine learner. So a machine learning person is much more powerful than a statistician and rather than an engineer. So we call that the data engineer. Okay, so we apply the machine learning technique. I will touch upon some kind of biasing. So what we try to do, as I mentioned, that the box plots to check that the data quality. And I mentioned that it used to provide summarized data set and is often used in exploited data analysis. It is a present data set, maybe 25th percentile and 75th percentile, as I mentioned, with a median and scattered plots. Then you have to have a quantile plot. These plots, it will give you a first hand preparation, what type of data you are doing for the analysis. Now see, I am showing you the box plot. So mean concentration for the iron and for the fluoride, these are the parameters they have given me. And then in this nitrate, you see nitrate is not normally distributed because this domain is not the same. So and it has a minimum value, it has a maximum value. Similarly, pH is almost normally distributed, and here it is a pH. So all these parameters, when you join together, so you may not be having any distribution at all. I cannot, because here I am seeing that they not normal distributed. Here I am assuming is a normal distributed. Here also not normal. So when you mix
So
up
what
all
is,
this,
excuse me, sir, what is TH?
TH is the total hardness. Total
Oh,
hardness.
total hardness. Okay.
So these are very important domain and realistic domain which I have already done last year. This year, because of the COVID pandemic, I still not continued.
This is very important, sir, for all
yes, very, very, very important. And lot of people, and after my analysis, some of the villages I do not mention, they have a really fluorosis problem and ricket problem. Now they are trying to recover because they understood that their drinking water is having a lot of fluoride, and you will surprise that the green tea also has a lot of fluoride. And reverse osmosis, if you do that, the backwater gives a lot of healthcare problem. So those things they came to know, and now still I think that next year, if it is travel is okay, then I have to go, and I'm mentoring that and doing my analysis. That's why it is a realistic example. Now see, I'm doing the water quality index by using this simple calculation. So this concentration they have given me from their laboratory analysis, and this is the concentration of IAT water quality. And as I mentioned that when we go for the index value, I have to, because to a media I cannot give the figure. I have to give that is some word which they understand, because whenever water quality is giving, it is discussed at the parliament, and from that parliament the decision will come. Parliament people will not understand what is 50, what is 100, but they will understand that it is an excellent, good water, poor water, very poor or unsuitable for drinking. This sentence they understand very well, and based on that they can be taking the decision. So analyst part is to give this value and feeding the part in a different way. So this kind of thing when we are doing, it is basically fuzzy estimation. So therefore the fuzzy part is an important for your time series data driven model, especially for water quality, air quality, photovoltaic sensor, all this. So therefore here I am showing some of these things. So 2010 to 11 and 2010, 17 to 18, these various districts, I have just shown some of the districts, and then I am showing you that the water quality is less than here, excellent, poor, all this kind, and then you'll see that in which district water quality is good and which district water quality is poor. So these are the district continued for the further value for the different series, and then the further districts are there, all the 27 districts are. So therefore we find it out that, and when you go for the analysis, you will see that how we can do that, because it's very important that you have to really go for the whether Gaussian or non-Gaussian. For example, I am showing a sparse Gaussian process can help with that is some kind of PD, and there are the issues I showed that the heterogeneity, non-stationarity, spike noise, change points, everything. And now see that the data acquisition and management is come from this. So everywhere your doubt may come, and everywhere that is, so you have to really go into the field, and instrumentation knowledge has to be updated by doing a lot of techniques like data logger, then link, data acquisition, and so on. This I am not doing, this is a different field as well. And then some kind of satellite data also has to be incorporated. So as I mentioned that all these information I have to feed a statistical machine learning model, and then quality model, and then we have to take for the decision. So they definitely is a temporal framework. So we have to apply the Lagrangian framework, because Eulerian framework is not possible, Newtonian framework is not possible. We have to go for the Lagrangian framework, because as you know, water network is a huge, it is connected everywhere. So today if you discharge water in your basin, it will be going to some other area, automatically is connected. So therefore Lagrangian framework, some stationary database is there. So you have to go for the data types, storage models, access methods, and snapshot model. So now you see when you try to connect all the pumping station at the different time, it is basically giving a flexibility that it is a graph theory. So I can apply the graph theory based data driven model. So that is why time expanded graph I have mentioned here. So these are the area where again FDP can be elaborately organized, because how the graph theory can be applied for a time series analysis, because very few people can be understand that the computer science I'm merging with the statistics and the mechanical engineering. So these are general framework, STN models for complex real world, novel network analysis models, and these are realistic examples which I carried out. That's why I love to show you that how a time series data driven model can be there. So when you have the STN data integration problem, heterogeneous multimodal networks can be there. There are time varying properties, correlation properties, and you see that all these different types of network can be. And finally, you can apply the GIS to get the landscape and land problem. Okay, so these are time series. So there's a temperature, stage, and dissolved oxygen, pH, turbidity, conductance. So everywhere the different times is. So you have to slice that which portion of the time I should take care to go for my water quality index. So therefore, water quality time series, as I mentioned, it contains the always missing information and how to recover the missing information. As I was telling, so this is my principal component analysis. This development took place alternating least square method, and it is a by chance. Then mathematics I did, and then algorithm developed, incorporated in the MATLAB, and find it out that it is a good technique. So therefore, many of this area, lot of these are the parameters missing was there. So we recovered, and this is the algorithm which I developed. And two MTech people they did last year, and now today they are in the Yahoo and Google using only this method after the development. They did last year with me, alternating least square method. So this is the algorithm, alternate least square method, and I need not go to the algorithm. Then again, for the mean concentration of water quality parameter after recovery of missing information. So these are the missing information because a lot of information was missed. So I recovered with that. So these are the samples are collected for the year. Approved statistical methods is given, and then you see after the missing, I calculated that the fluoride mean and standard deviation, nitrate, pH, TDS is the total dissolved solids, then pH total hardness. So all parameters for the different year I calculated. So every year you can always apply those formula for water quality index, and then you see which year it is getting deteriorated. If you can find it out which year it is getting deteriorated, you have to precaution that the ministry level that yes, water is getting deteriorated. So evaluation of water quality is defined as a sum of, we already mentioned that as I showed that the two methods I carried out for them, machine learning. Of course, the job is not yet over; it is going on. And not only that, one interesting things I find it out when we go for the water collection, we find it out is a very interesting. At the geological point, two rocks are there, and both the rocks upper surface that the water was flowing, but inside the rock there is a sample of water which is drinkable and so cool that water and not at all having any bad quality of water. So those things from the geological point, if we can collect, that is the very thing. If we can pump that, and if we can apply a pump there and pump those fresh water, it will be good for the villagers. So this is the analysis study. So this is the challenges you see that the highly non-stationary, highly non-linear, many changes in dynamics. In general, our models need to be general, flexible, robust, interpretable, fast and efficient, and easy to set up and use. So these are the incorporation should be taken care when you try to do the model. So therefore, as I mentioned that sensor may be faulty. So if the sensor is faulty, that means Gaussian distribution is closed under affine transformation. So data is not normally distributed, not Gaussian distributed, but some kind of transformation. So we have to really judge that whether the affine transformation or not. So therefore, we have to apply a conditional mode technique. So this is the conditional mode technique which I'll be talking tomorrow in detail for the Kalman filter. Why Kalman filter is important for developing this kind of sensory fault. So here you see that the sensor that under the constant, you have the auto correlation, and then this is the auto correlation technique. We can show that the tomorrow itself when you go for the Kalman filter, and then we have the struct sensor, the output. So this kind of control chart is available for any kind of plant, and from there only we have to understand really whether it is a faulty or not. So these are struct sensor. This one is sensor offset. Then these are sensor drift. So the sensor drift will be there, is a really very good technique. And then finally we go for the different network technique. And these are supervised approach, the supervised extension to Bayesian online change point detection algorithm. So these algorithm basically we applied the BOCPD for finding the which kind of faulty it will be there. So here you see that there are some example I showed here. Some samples can be taken from here, some samples can be considered, some of the spikes, if for understanding we can do. So this kind of algorithm is applied to understand where the faulty may be there. Is the change point detection basically. So with the help of that, as you mentioned that, if I go to this slide, I understand there is a Bayesian technique, okay? Because probability of occurrence of Y condition that the time is given. So with respect to that, we go for a maximum a posteriori estimation. Here we know that it is a Bayesian technique. So you have to apply the posterior probability, which is nothing but my likelihood multiplied by the prior probability. So the prior probability I do not know. Likelihood come from the maximum likelihood estimation. Yesterday I showed you. Prior probability you have to guess. So you go on multiply and then make this second step is a posterior probability, and then again that the posterior probability is the prior, and likelihood is already given from the data. So if you continue this iterative process, you will come up to the convergence technique, convergence method, and that will be your actually posterior probability, which is called as a belief. With the help of that belief, you can justify your system. That means your model is prepared. So here I am showing that the one cancer related problem, the probability of positive, no cancer, which is given here, probability of negative for no cancer. So various probability. And then with respect to that, by using the Bayesian technique, we can really find it out if the probability of cancer is there when positiveness of the medicine is there. So how much is there? From there, we can easily find it out in a particular community whether cancer is genetic or not. Same kind of thing we can apply for the COVID to understand is it a community transmission or not. So basic thing is that we wanted to do the maximum a posteriori estimate. In the maximum likelihood, we have taken the likelihood as a yesterday I mentioned is simple like that your multiplication. So in this case, what you try to do, this is my posterior probability, which I am trying to calculate by likelihood coming from the data, and this is prior, which I am guessing. And this guess I am tuning by this technique. Okay, so I am showing you that this is my posterior probability, this expression, since that the probability is normalized, so most of this thing experiment will be there. So that my estimated of the parameter using this maximum a posteriori method is nothing but my estimation of that. So you basically maximize. So that means after the maximization, what to do? You take a log. If you take the log, so now this kind of thing I have already explained. So you are taking the log. If you take the log, you have the summation. So ultimately, you have to do this kind of process, and here another process. So two processes are there. So now you see that the probability of hypothesis condition your data is there, which I can map here. So what is to be done? It is a computational intensive. It is basically learning. So that means I am not depending on my data. Data is given once, and then I am learning from the data. And as I'm learning, try to important, I can temporarily produce the yes, the data should be had. So I'm correcting the data also. That is an advantage. So it is my geometric expression. I'm showing an example how to do that. So this condition is multiplied by this. Now you see that this is coming from the data, which I'm giving here this expression, which is geometric. And this is my probability distribution, is a prior. So prior taken up. If I do that, I will get this expression. Now my aim is that I have to differentiate after taking the log. And if I do that, so I'll get that the x is equal to 2 by 5. So that means with respect to this, even though my geometric data is there, I can easily find it out what is my actual value of the data. So this is again, I call it as a data quality technique. Okay, because you understood what should be the value of x. So this is again thumbtack problem. Theta ml yesterday I was showing that this value, and then today if I try to go for the map estimation, you will get that the theta map is 6/7. So slight corrections is possible here. So therefore, this kind of thing we apply for some economics to understand that whether the demonetization is benefited or not. I am not showing the actual data, but this particular technique we applied for that and find it out demonetization was not benefited. Okay. So this is a Bernoulli distribution. This is a likelihood, and this is my actually your prior distribution. Why beta? Because whenever I try to do the likelihood function, if it is a Bernoulli, the prior should be the conjugate of that. So conjugate distribution of the likelihood distribution is a Bernoulli. If it is a beta. Similarly, if it is a normal, it is a normal. If it is a gamma, it is a Poisson. So like that, only conjugate distribution should be there. That list is already available in standard literature. So if I try to do that by using the same technique, so we go for the beta estimation of this equation. Okay, I'm not going to the detail because it's very simple understanding that take the log and then take the differentiation. If I do that, the del of log beta, you will get this expression. And then if you make equal to 0, I got my new map estimation is this. So with respect to that, now we know that how many points are there and what is the value of alpha and beta. You can easily find it out. So you see that the 100 times you have done, and NR is 93 and alpha value beta. Now ML, if you see, it is all the time constant. So there is a certain problem in the ML, but in the math, if you go in certain location, the 99.3 is not there. So that means mu map is giving you the flexible method of data quality. So that is why maximum estimation should be adopted for data quality. So map estimation procedure allows to inject our prior beliefs about the parameter values in the new estimate. With respect to that, I think I could complete that within the stipulated time. It is a 9:15. Thank you very much. So I have completed. Is there any
Yes.
question? Yeah.
Thank you, sir.
Yes,
Thank
thank
you
you.
so much. We are really like spellbound with your lectures when you are delivering, because really when we are dealing with data, some sensor data we are taking from different instruments, and we are trying to make a pilot plan for photovoltaics with different
Yes.
sensor data from for weather monitoring, and
Yes.
even water quality agriculture is our future applications, whether we can do or not, even to solar cell fabrication. Maybe the technology will be adopting
Hello.
in future. So
বলো।
in
ঠিক আছে? আচ্ছা। হ্যাঁ। ঠিক আছে। হ্যাঁ। ঠিক আছে। আমি তোমাকে খানিকক্ষণ পরে কন্ট্যাক্ট করছি। হ্যাঁ? ঠিক আছে? আচ্ছা, ঠিক আছে।
I think, sir, it is really very important to know everything for us, not only for computer science because they are doing with other things, but for the hardware quality control and monitoring is our approach. In every cases we require this, even for fabrication also. What the yield is coming, how the
Yeah.
quality of the wafer is coming, every time we require.
Yeah.
So even the quality of film, produced film, water quality of nano materials, quality everywhere we require some quality that yes, the data is the outcome is the data.
Yeah.
And
That is why.
even I can remember one problem, sir, that was once the best paper or best theme in radio physics. I have given a conference paper and it was presented in not orally, it was given in the display section. And I can remember that the convener is telling
ঠিক
that
আছে।
I asking him that why not in
ঠিক
oral
আছে।
presentation? Why you have
আমি
given me
কন্ট্যাক্ট করছি।
in this like poster presentation? Then the seniors, the senior professors, they are telling that in abroad, when there is new thing is coming, generally they are display it in the poster, not in oral, because oral is for a session and maybe parallel sessions are going on, so you may not may miss your presentation. But as it is posters, everyone is looking on the poster, and those who requires, they will at least like see and what is happening, they will ask you. And one problem that I can remember, sir, I can estimate the problem was band gap empirical relation for the band gap of nitrates.
Okay.
At the year of 2005, I have communicated that paper and my single authorship. And actually the thing is, I have discussed so many times with Professor Nag, my guide, and we are in a paper that we want to publish the indium nitride band gap. At that time, the band gap was anomalous because some experimentation is going on and different experiment is coming up with different values of the band gap. So how to estimate the band gap of that and what will be the estimation for the new material band gap with nitride component. So I collected all experimental data of aluminum nitride, gallium nitride and indium nitride, and I have put that least square fit method, but I don't know that was the name was the statistical method, and that I just want to fit that if I make a linear line with that and if I can estimate how much error is actually there to fit the linear curve and to find the coefficients, and after that I have found out that coefficients and that coefficient, and from there I have estimated the boron nitride band gap. And I can remember that one very important person, Umesh Mishra, he was very famous in nitride fabrications, and he told at that time he came in that conference for invited talk, and he told that it is a very important paper for industry. And I stood at that time, it was not awarded for the poster presentation and oral presentation, so I have not got any award for that, but they have given me one certification that your paper was very good and you should communicate in the journal. So I can remember that thing. So I was really, sir, very much motivated to take different approaches of machine learning, statistical learning
Yes.
for our semiconductor as well as system design, for our manufacturing, for our characterization technique, because all our data involved program. So in that case, sir, we think that in future also we'll be taking your help and your FDP program that you are.
Sure, definitely.
Now my questions are 2-3 questions from participant, and can I ask two or
Yeah. So
that
come
one?
in. Yeah.
Yes, one important question that you were telling, that statistical approach and machine learning approach.
Right.
So the thing is, what is the difference? Is there any difference? I think there is no difference. But what is the demarcation line between estimation and forecasting? Is there any accurate demarcation?
Yeah. First question answer is that there is a lot of difference between statistical techniques and machine learning techniques. Okay. Statistical techniques are not having any learning facility, but machine learning techniques, as it is a learning what is there, it is learning. So that means we try to adjust our model with respect to the data. We are learning so many things from the data. But in case of the statistical analysis, it is just static. That means once you have done, it is done. But again, if your data changes, again you have to apply the complete from the very beginning. So the main difference between statistical analysis and machine learning, in the statistical learning, there is no memory involved, but in the machine learning, there is a memory involved. So that is the difference.
Okay, sir, can I say something about this? That I think that actually the model or learning process we are adopting here in statistical learning, that we are adapting and we are designing, because when we are making the linear regression, we are thinking that yes, from the features of scatter plot or anything, we are designing the model, and from that model we are
No. Sometimes may not, because you see that if I try to find it out the relation between fluoride and nitrate, I cannot. If I try to
okay.
find out the fluoride can be represented by pH or TDS or any other thing, I cannot. So therefore, there is no connectivity between fluoride, nitrate, pH, and this in the field of the water quality. But even though we are trying to do that, the connection is network by neural network or deep learning, we can make a model. So that
Okay.
cannot be
So,
done by the statistical analysis.
okay,
That is the
okay.
difference.
So
That
that
is the,
means if there is no pattern, we are unable to find out.
yeah,
So
yes.
in that case, we will be going for
No, the machine
machine
learning
learning
technique.
or deep
Okay.
learning.
Yeah.
But if there is an easy pattern that a human
Then
can
no need,
understand or perceive, no need.
no
Okay.
need. Okay. So the second question is that the estimation theory and forecasting. Forecasting estimation theory is a statistical process, right? But forecasting is not the statistical process purely, because here you are giving some kind of future behavior. So right from the present and past, you are trying to predict that the future. But in case of the estimation, you are working on the present. That's all. Not past, not future.
So that means within the range we can estimate,
Yes.
but beyond the range,
Beyond the range, you
extrapolate or interpolation kind of thing.
no.
But that means beyond our limit, we cannot expect what is happening. So in that case, we have to adopt machine learning or deep
machine
learning.
learning. Yes, deep learning.
Okay. And the other thing, what you were telling about that R-square statistics,
Yes.
R-square values, okay, and degree of freedom and confidence interval. Okay, sir, that what is confidence interval and how can we
confidence
confident
interval?
about
Confidence interval. There the how low value of a system is changing your total system. That is called the significance level, which is known as the alpha, the left hand side portion of the Gaussian distribution. Now, if your alpha is 0.05, that means your confidence level is 0.95, because 100 minus 0.05 is your 0.95. So 95% confidence level measurement is nothing but you have fixed your lower limit and you have fixed your upper limit. So your all sorts of measurement will follow within these two limits, lower control limit and upper control limit. Lower control limit is at the x bar, that is mu, minus your z value of 1.95, which is a 95 constant, multiplied by standard deviation, and upper control limit is the mean plus 1.95 into the sigma. Sigma is the standard deviation of the data set. That's all. So these are confidence level. Okay. And degree of freedom is the total number of observation minus 1. Why minus 1? Because only you are taking one explanatory variables, which is nothing but the mean. You are only observing the mean of the data set. But if you are observing that the many more parameters, say k explanatory variables, then your degree of freedom will be the total number of observations minus k. That is, degree of freedom in general is total number of observations minus number of explanatory variables. That's all. So this is the difference.
okay. Uh, that is a degree of freedom.
That is the degree of freedom. And confidence level I mentioned here. That's all.
Okay. So then before going to start any kind of data-driven model from any data generating point, so can we apply first the box plot? First,
Yes,
what you
always box plot. Always box plot.
then we can conclude, not conclude, but your advice, because I am only learning that box plot and the variance and covariance. Okay, these are these three, along with some kind of like freedom, degree of freedom, and how many parameters we are going to handle. These are the, can you, sir, chalk out that these are the fundamental things.
These are the fundamental things.
These are the fundamental things. So before selecting that, we have to know. And the one important question you have seen in your data error, that sensor and the plant pilot plant quality, that you are telling that before, how do you know that the instrument, because offset, calibration, everything is done by the instrument person. Okay. So they are providing us the first time we are using it. So before going to the plant, say plant is like in our case, maybe in photovoltaic plant, photothermal plant, or with so many sensors, because it are the these are along with different electronic instrumentation, converter, battery, everything. So they are generating a huge number of data, mostly the input parameters are coming from the electronic parameter and some weather parameters, meteorological parameters. So taking so many parameters, the outcome we are getting. So now if we are trying to make the plant as a pilot plant, so we have to generate that kind of data sheet, manual, everything, and the data quality first we have. So in that case, before going to the plant, how do you ensure that yes, our data is perfectly coming?
So that is why you have to do the error analysis. Na? You have to calculate the error analysis, and then you see that how much of error in your data is there. So you have to deal with that error wherever you are mentioning your data set. That's all. You have
Error
to do
means
that.
then we have to require a standard parameter or like this. How
No,
do
no,
you
no,
know
no.
that it should be,
You collect the data for a 24 hours, and then
okay?
you try to find out the standard error of the data by taking the standard deviation divided by the square root of 24. So like that only you calculate the error. And if you have seen that the instruments are connected to another instrument, you calculate the error of that instrument. And this is based on your Poisson statistics. Okay, so whatever the measured data you have, then you propagate that error by using the error propagation formula, and then design what should be the actual error of the total instrumentation. That you have to maintain throughout the lifetime of the instrument. That's all.
Okay. And in every case, we should, if we make the plot and everything, then we can
Yeah,
know that
yeah,
when it will be failing.
yes,
The
yeah,
failure is occurred. So in that case, we have to report.
yes, you have
To calibrate it again.
yes. Again, you have to calibrate.
Okay. And the last and from my part, one important question that is regarding that you were telling about. mm, One is multi-dimensional technique,
Hmm.
dimension reduction and multi-dimension. It is the
Dimension is that the
question that,
number of variables are more. That is the multi-dimension.
yes, and in most cases, environmental parameters and the outcome
Yes,
is
so
depending
many
on that.
parameters are. There is the
So we have to,
multi-dimension.
first reduce that. What are the most important parameters?
Exactly, exactly.
Okay, okay, that is the theme of that.
Yeah, that is the theme of that.
Okay, sir, thank you. And any more question from the audience? That means the from the participants. If you please, sir, any question? Sir, sir, if you give us the link of your PPT, and please, organizer, if you post the video, so then everyone can learn it.
Yeah,
Yeah,
yeah. Yeah, I
focus.
will I will send the PPT in the form of a PDF. Then you can post it to the everywhere
Okay,
wherever you like. Okay.
okay, sir.
Okay,
So,
so thank you, Professor Dotto, for his nice intellectual and proficient talk in the area of data-driven model. So thank you, sir, very much. So we can next shift to the for the sessional talk of Professor Sinha.
Yeah.
So, Madam, so I would like to introduce Professor Sinha a bit,
yes, yes, yes.
and then I would request Professor Sinha to have his talk.
Yeah.
So, we the people from MAKAUT, starting from the students and the faculties, everyone knows the eminency of Professor Sinha in the field of teaching VLSI design as well as signals and systems. He has the proficiency and authority in teaching several trending fields of VLSI like DSP, digital signal processing, VLSI system design, DSP processor design, as well as also in computer architecture also. He is currently serving our university as a director of academic reforms. He is also UGC appointed adjunct faculty in Department of Microelectronics and VLSI Technology in Maulana Abul Kalam Azad University. Earlier, he has several years of active experience as director in our MAKAUT. Before that, he has the glory of significant teaching experience in IIEST Shibpur for several working years, as well as in overseas institutes in Canada. He has also served the dignified and esteemed chair of directors and other higher posts in several national and internationally eminent industrial organizations and academic institutes. Besides, he has more than 30 years of research experience. His areas of research interests are VLSI design, DSP, processor architecture, and reconfigurable computing. He has published numerous papers in several internationally renowned journals, especially in IEEE transactions and in several reputed conferences. He has been awarded with FIE International Scholarship. He has been honored as Fellow of Institute of Engineers in 2013. Moreover, he has been awarded with Indian Leadership Award for Education Excellence from Indian Economy Development and Research Association, New Delhi in 2013. So we can explore his vast knowledge and experience in his specialized field of signals and systems, and therefore the application of time series data analysis to investigate the physiognomies of signals and systems. Therefore, I have the most modest request to Professor Sinha to represent his lecture topics of today on algorithm of time domain signals. Sir, please.
Thank you, Bhushaji.
Thank you, sir. You're most welcome to take the session and deliver your speech.
Can you see the presentation?
Yes, sir.
Yes, sir.
Yeah, it's okay, sir.
Yes. Yeah. So the topic is time domain signal analysis. Before me, Professor Datta, in fact, for the last couple of days, have been talking about data-driven model forecastings. So here, in fact, we'll be discussing signal analysis and try to see, how this time domain signal analysis can be made fruitful for different data-driven analysis as well. So first, let's have a look at the basic concepts on time domain signal analysis. I believe, in fact, all of you are quite familiar with that, but still, I'm trying to recollect those concepts once again in a different way. In fact, each and every part of our life is somehow linked with the products or services or economy related to signals and systems. There are various products, right from low-end consumer products to high-end industrial and military products like air traffic control, submarine detections, ballistic missiles, nuclear reactor. These are all of the examples of the high-end applications of signals and systems. Basically, digital signal processing is one area that is offshoot from signals and systems. And we can see the low-end consumer products like television, video camera, washing machine. So all are basically the products of digital signal processing, which has come basically from signals and systems. However, time domain analysis is not only important for only product development, it is a very important tool for business forecasting also. In fact, forecasting model, Professor Datta has been talking for the last couple of days very nicely. We understood is forecasting. So this, in fact, this time analysis data-driven model would be made useful for the basis for understanding past behavior and forecast future activities, planning for future operations, evaluate current accomplishments, evaluation of performance, estimation of trade supply. Even there are examples of stock price, exchange rate, interest rate, inflation rate, national GDP. All these are basically, in fact, the applications of data analysis. So here are also a number of applications. Now, so when we talk about signals, and we're talking about time domain signals, so let's have a look at what the signal is. In fact, our motivation is basically to describe signals, both man-made and naturally occurring. So in fact, the subject, signals and system, deals with mathematical methods used to classify the signals and to analyze the signal and to synthesize the systems. So what is signal? In one word, we can say that signals are variables that carry information, and systems process input signals to produce output signals. Okay? Definitely, when the output is producing a signal, that should be governed by a law. So the system processes the input signals to produce output, and there must be mathematical methods on which the input signal will be converted to output signal. So examples of signals would be electrical signals, like your voltage or current in a circuit, acoustic signals, audio or speech signals, could be analog, could be digital, video signals, biological signals like sequence of bases in a gene, mechanical systems like vibration in mechanical systems, biomedical signals, EEG, ECG, etc. So these are the examples of the signals. So generally time. Excuse me. Now time is used generally to represent the independent variable signal. So if we draw the curve, one is the x-axis and the y-axis. X-axis is the time and y-axis is the value at a particular instant. So this xt or ft, which is a function of time. So independent variable may be spatial variable in image. Spatial variable means the coordinate basically. And here color information is also specified as a function of the positions. So independent variables can be continuous, like trajectory of a space shuttle, mass density in a cross section of brain, can be discrete, DNA-based sequences, digital image pixels, can be 1D, 2D, ND. So continuous time signals, xt, t is a continuous variable, and discrete time signals, xn, n is integer only. So this is an example of continuous time signals. So there is no break. In fact, for any value of t, we'll get xt. That is the continuous signals. So most of the signals in the physical world are continuous signals. The voltage, current, pressure, temperature, velocity, all are in fact examples of continuous time signals. So discrete time signals. Discrete time signals, in fact, they are made basically. So continuous time signals are sampled and then digitized, and we get the discrete time signals. If we see here, so n is x-axis and xn is a y-axis. So at a given instant n, so n here in fact integer. N cannot be like 0.5 or 2.5. So 0, 1, 2, 3 in that way. So time is basically here discretized. Okay. And if you see here at a regular interval, the values of xt in the continuous domain are sampled, and we are getting x0, x1, x2 in that way. So here small t equal to n into capital T, where capital T is known as a sampling period. Okay. So examples of discrete time signals in nature: DNA-based sequence, population of energy generation. So knowing the signals, let's have a look at what the system is. So as we have already discussed, that system has an input, system has an output, and system has a behavior. By virtue of the behavior, input is translated to output. So for continuous, if xt is the input, yt is the output, and for discrete time system, xn is the input and yn is the output. So examples of systems: dynamics of an aircraft or space vehicle, an algorithm for analyzing financial and economical factors to predict bond prices, an algorithm for post-flight analysis of a space launch, or edge detection algorithm for medical images. So here, in a simpler fashion, let's try to understand what is a continuous systems and how this continuous systems is converted to a discrete systems. Take the example of this RC circuit. So input is a raw signal, and since this is basically a low-pass filter, output will be a smooth signal. So V in T, that is given at the input, and across the capacitance, we are getting V out T. So the equations will be input V in T will be equal to V out T plus voltage across resistors, that is RC dV dt. Okay, yes. And this can be converted to discrete. Like if I say that input is Xn and output is Yn, then this difference equation can be formed. So here, this differential equations like dv out we can write like Yn minus 1. And del T is basically the sampling time. So dt can be written as del T. So in that way, we can form these difference equations. And from the difference equations, easily we can make this circuit. Okay, and this is a discrete circuit, which is based on the digital circuit. So here we require adder, multiplier, and the delay units. Delay is what? Like Yn minus 1 and Yn. So what is the relations between Yn and Yn minus 1? So if Yn is input of any systems, then the delay will produce Yn minus 1. That is unit delay. So if we want the delay of, let's say, input is Yn and output is Yn minus 2, so 2 delay will be connected in cascade. So easily, in fact, a continuous time signals or continuous time systems can be converted to a discrete systems by converting the differential equations to a difference equations. So as we talk about sampling, so sampling continuous time signals to obtain discrete time signals, how it could be done? So discrete time signals are obtained by sampling the continuous time signals at regular interval t. And t is called the sampling period. And this sampling period, how it is determined? It is determined by Nyquist sampling theorem. And what is Nyquist sampling theorem? In a signal, in any aperiodic signal, if there is a maximum frequency, if max, then sampling frequency should be greater than or equal to twice f max. And for a continuous time signal xt, the equivalent discrete versions is xn. So n is an integer. Value will be 0, 1, 2, 3, and so on. So small t equal to n into capital T. So this sampling process is basically what? Is multiplying xt by the sampling functions. So first, without going into mathematics, just if we look at it physically, what is happening? We are sampling this continuous signal at a regular interval. So at a regular interval, pulse 10 should be coming of very small width. So width will be almost like 0. So if we multiply this pulse 10 by this frequency, by these signals, then what we'll get at that particular instant, we'll get some values. So if xpt is the sample values, then xt is multiplied by pt. Pt is nothing but a pulse 10. So this pulse 10 can be denoted as delta t minus nt, where n equal to 0, 1, 2, 3, etc. So sampling can be obtained by just multiplying the continuous time signal with a pulse 10. After that, we have to quantize. So these sample values should be quantized. Basically, these things are done by digital analog to digital converter, commonly known as ADC. And here, in fact, the quantizations, what should be the perfection of the quantizations value? That depends on by how many bits we are representing it. Okay, so if there are capital N bits, then there will be 2 to the power n digital values, and in fact, resolutions will be governed by number of bits. After that, the value has to be coded. It could be in binary form, typically, or binary coded decimals, or in any coded form. Now let's take the example of a mechanical systems. Interestingly, these mechanical systems, The equations will be very similar to our electrical systems as well. So here, let's say spring K, a damper D, and a mass M. And if xt is the force applied to it, the right hand directions, then what will happen? This damper will give the resistance and spring this energy that we used here. So this is the equation, second order differential equations, m into d2y dt square, or yt is the displacement. This will be given by this. So this is a second order differential equation. So systems, in the sense we can say that what is the input and what is the output? Input is the force, excitation functions, xt is applied on this mass, and displacement yt can be viewed as the output, that is the result. So here this is the equation, and the solution of these differential equations will give yt. In fact, this can be modeled in using Laplace transforms. If we just find out the transfer function hs, which is ys by xs, then we have to take the Laplace transforms the whole thing. So this time domain function will be converted to a frequency domain, and then we'll be able to find out this transfer function. And this transfer function, in fact, denotes the behavior of this system. And these are the parameters like all these values, m, k, d. These are equivalent electrical systems. So systems can be interconnected as well. So there are basically three types of connections. One is the cascade, parallel, and feedback. Now, parallel has an advantage. Now, when these systems are designed using digital computer systems, then some execution time will be required for all these blocks. Now, when these systems are divided into two subsystems, are connected parallelly, then in fact execution time will be reduced, because that will be shared by both the subsystems. Now, first, let's have a look at some important functions. So when we will be analyzing the signals in time domain, we have to deal with some important functions like cos omega t, sin omega t, unit step functions, ut, impulse function, del t, impulse strength. So these are the generalized functions. We'll see what are these functions and what are their behaviors. So impulse function. What is the impulse function? In mechanical systems, let's say delta t is a force. Then what is the total impulse of the force? That can be measured by I tau equal to del t dt. So typically it will be del t dt. So lower limit will be t0 minus tau, t0 plus tau. So this tau is very small in fact. So del t will have some value c, that is t0 minus tau to t0 plus tau, and otherwise it will be 0. So then I tau will be integrating this, we will get 2 tau into c. Now, if this c equal to 1 by 2 tau, then I tau will be 1, which is independent of tau. So this can be viewed as unit impulse. Now, here, if you see this diagram here on the right hand sides, you find that del t equal to 1 by 2 tau for this, otherwise it is 0. So in fact, if this rectangle, okay, in y-axis there is a height and x-axis is a base. So if the base is reduced, and then the height will be increased. So when it is almost like 0, very close to 0, then the height will be almost like infinity. So for t equal to 0, limit del tau t becomes infinity. So this is the concept of impulse function. So from here, direct delta functions was derived. So we can say that del t equal to 0 for t not equal to 0, and del t equal to infinity for t equal to 0, and del tau dt equal to 1. That means area will be 1. Now, since area is 1, then when this at t equal to 0, then height will be infinite because area is 1. So this is the definition. So three things are there. Del t equal to 0 for t not equal to 0, del t equal to infinity for t equal to 0, and del t dt equal to 1. That means the area is 1 from minus infinity to plus infinity. So this is a very important concept for delta functions. And delta function plays a very important role in analyzing the signals. So formally, these are. So this direct delta function is also called unit impulse function. Unit impulse because the area is 1. Now, generalized function. The value of delta function can also be defined in the sense of generalized function. Now here, del t, phi t dt. Phi t is a function equal to phi 0. Now, mathematically it can be proved, even if we see physically, concept-wise. Phi, this is phi 0. Phi 0 means what? The value of phi t at t equal to 0. Now, since del t equal to 0, for all the values other than t equal to 0, so in fact, this multiplication will not yield any results. So only at t equal to 0, this phi t, and del t dt is basically 1. So this is phi 0. So this is property of unit impulse function. If it is shifted by t0, then it becomes phi t0. Just you can write t as t plus t0. That means shifting these impulse functions and multiplying it with phi t, and if we integrate it, it becomes this. So properties of unit impulse functions is, we're not going for the proof. So this is also very important property. Ft dt equal to f0 dt. That comes from the previous one. Okay, I'm just skipping this thing. These are the standard properties of unit impulse function. So Ft dt equal to f0 into dt, and del at equal to 1 by a mod del t. Now this will be useful for some of the. I'm just skipping these things. This is a product rule. If we differentiate it, so, and straight away we will go to the unit step function. So unit step functions, basically it's a discontinuous function. If we see that from minus infinity to 0, the value is 0. All of a sudden at t equal to 0, it becomes 1. That's why ut equal to 1 for t greater than equal to 0. Here it is written greater than 0, it should be greater than equal to 0. And it is 0 when t is less than 0. So ut phi t dt is basically phi t into dt, because ut is 1. So the limit from minus infinity to plus infinity, now it gets changed to 0 to infinity. Because it exists from 0, the value is 1. Now ut is plays very important role in signal analysis. Let's say a sine function or cosine functions. Basically, sine or cosine function starting from minus infinity and goes to plus infinity. But to make it causal, means the real, we have to multiply it by ut. So once we are multiplying this sine or cosine function by ut, then from minus infinity to 0, this value will be 0. So basically it's starting from 0. For synchronization purpose also, it is very important to multiply any sine or cosine functions with ut. Now differentiator. Now differentiator, basically if xt is the input, the differentiator will produce dxt dt. So here in the right hand side, we are giving the circuits using an operational amplifier, capacitance, and resistance. This differentiator can be formed. So impulse response. So if input is an impulse, and if we take the differentiation of that, that is called doublet. And if we take the convolutions of doublet xt, it gives you dxt dt. So in that way, by connecting the differentiator in cascade, nth order differentiations can be formed. So derivative of the unit step. So if we take the derivative of unit step functions, we will get del t. That means impulse functions can be obtained by taking the derivatives of the unit impulse. Now this, if we just see this, we can view this ut as the summations of del t, okay, at different points of time. So delayed del t's, and by adding them, we can get ut. So if we differentiate this, what will we get? Definitely we will get an impulse. So this is the derivative of, so this unit step can be given at the input of this circuit, and we'll get del t. Now, in practical example, this, let's consider a circuit. A small resistor is there, a battery is there, and a switch. When the switch is on, then what is happening? It is generating ut, and that ut, if you give at the input and output, we'll be getting this del t. And how sharp it will be, it depends on the RC time constant. Similarly, integrator will give the integrations of the input, and again, this also can be designed using RC and an operational amplifier. So multiple integrators can be connected in cascade. So if we give d2x dt square at the input of the first integrator, we'll get dx dt and finally x. So now looking at these basic signals like impulse functions, step functions, what are the desirable characteristics of the state of basic signals? We can use large and useful signals by these building blocks. That means using these, we can make other signals also. So if we want to make the synthetic signals using these impulse functions, we can make it. So just look at this diagram. First, if we have an impulse, then if we integrate it, we'll get ut. Ut, if we integrate, we'll get tut. That is the equation of a straight line passing through origin. Further, if we integrate it, we'll get a parabola. In that way, we can make various kinds of signals. And again, from these signals, by extracting some informations, we can make other signals as well. So these are the basic principles of sine and cosine generations. From the Euler's formula, e to the power j theta, the mathematicians say I. So basically is e to the power j theta, which is equal to cos theta plus sine theta, or cos phi plus sine phi. One is in horizontal direction, another is at a 90 degree. So the angle, what is being made is omega into t at a particular instant. So omega is radian per second. We all know all these things. So now generation of the sinusoidal signal, let's see. Now here, if we just look at the equation of a simple harmonic motion, d2y t dt square plus omega c square yt equal to 0. Now interestingly, if we write that yt equal to, let's say, sine omega t. So sine omega t 2 times, if we just give the differentiations, what will get? We'll get this form of equations. If we write yt equal to sine omega t, then dyt dt will be omega cos omega t. Then d2yt dt square will be minus omega square sine omega t, that is equal to minus omega square yt. So the solutions is this. So solutions of this differential equation is this. That means sine function has the characteristics. If you take the differentiation two times, then you will get the same functions, of course with the minus sign. But interestingly, if you take e to the power j theta or e to the power j omega t as a function, and if you take the differentiation 2 times, you will get the same function. So that means the differential equation which gives d2yt dt square plus omega c square yt is basically the equation of a simple motion. We are getting 2 solutions. One is e to the power j theta, another is the sine or cosine. Exactly, in fact. So the solution of this differential equations, when you get the pure sine or cosine, this is a special case. Let's say the typical solutions of this is a plus b cos of omega c t plus j a minus b sine of omega c t. That is a generalized solutions. And from generalized solutions, if we take the special cases, we get yt equal to a to the power j omega c t, or b to the power minus j omega c t, or 2a cos omega c t, or 2b cos omega c t. In this case, a could be 1 or a could be half. So this is the generation of the sine functions. Now this is the mathematics of the sine functions. Now this how this mathematics can be implemented to circuit. So this is here. If we assume that x double differentiation is here, then we will get x dot, then we will get x. Then it will be to make it a sign change, do that and give it the input. So these are basically sine wave generators. So this has come from md2x dt square equal to minus kx, equation of the simple harmonic motion. And here this will k equal to omega square. So need of damped functions. Now from sine functions, if we want to make a damped sine wave, how to do it? Now for many cases in engineering applications, vibration is undesirable, wasting of energy and creating unwanted sound. For example, the vibrational motions of engines, electrical rotating machines, mechanical device in operations. So these things, in fact, they are not desirable. In fact, even sound or pressure signals are generated by vibrating structures. So how these things can be done then? So when a function like vibration is not wanted, then we have to diminish that. How it could be done? We have to get this kind of function. This is called damped sine wave. Now, how this damped sine wave can be done? Can be generated? If you multiply it by an exponential, decaying exponential functions, then we'll be getting like that. So decaying exponential function is this. So when xt is multiplied by e to the power minus kt, and of course with another multiplications with ut. So when you are multiplying with ut, what is happening? It starts from 0. And when you are multiplying e to the power with e to the power minus kt, then it becomes a damped function. So these are applications of this multiplications with e to the power minus kt, exponential function decaying. So we, in fact, the electrical engineers, we call it modulation of sinusoidal signal with exponential signal. Then producing different signals with step functions. Now let's say this is ut is a step function, and ut minus 1 is a delayed step function, one delay. So if we subtract ut minus 1 from ut, we'll get a small pulse. Similarly, we can make some kind of triangular waveform using this. So response of continuous time linear system. So response is if xt is the input and yt is the output, then the behavior of the systems will determine what value we'll get at the output. So this is in fact determined by the behavior of the system. In fact, convolutions determines the convolutions of xt with ht gives you the value yt. So this is typically, we all know that if xt equal to xt del t minus tau d tau. So xt can be represented like that, and then yt will be this x tau ht minus tau d tau. So h tau is basically when input is del tau, then whatever will be the output, that is called ht, means impulse response. ht is basically impulse response. So impulse response is what? If input is an impulse, then the response to that will be known as impulse response. So instead of xt, if we apply del t, then y2 will become ht. So these are the properties of that. I'm not going into details of the properties of that. We all know that is a commutative property and distributed property. Associative property. Now, so discrete time systems is basically saying if linear property means for x1n, if input is x1n and output is y1n, and for x2n, so xn equal to, let's say, alpha x1n plus beta x2n, and output will be alpha y1n plus beta y2n. So of course y1n corresponds to x1n and y2 gives output for x2n. So time invariant. So if input is shifted by n0, output will also be shifted by n0. And stability, that's a very important factor, that if yn is the response of an input xn, and if xn is less than px for all values of n, then yn also in fact should be less than equal to by for all values. So this is for bounded input and bounded output. So input is bounded, output is also bounded. We call Bibo stability. And causality, in a causal system, in fact, output cannot depend on the present input. Okay, and for n greater than n0, like below 0, in fact before 0, all the values output will be 0. So these are the representations. So this is convolutions. You can think like that, like del n minus k, hk. Then xn equal to, we can write xk.
Hello, sir. Hello.
Hello.
Sir,
Hello.
can I say something about this circuit representation, as maybe we will be missing in future? So that you were telling about that input and output, when you are dealing with the impulse functions or maybe step function, there is a circuit representation you are showing. So now when the e to the power minus at, that means the exponential decay, that how do you represent that? It is a kind of RC distant circuit kind of thing. How you write e to the power minus at into the xt.
Yeah, in fact, I was about to tell all. I was about to tell all these things. Since you have asked in between, let me tell you, e to the power minus kt can be generated by any circuits R and C.
Yes, that I am telling. RC circuit will be
Any RC circuit will do that.
Yes.
RC circuit cannot generate voltage. That's why we use the operational amplifier basically. Okay. So in the operational amplifier, if we use R and C, then what will happen? The output will be in fact decaying exponentially, and this can be multiplied by a sine function. So if you have a multiplier, and multiplier has two inputs, one input is a sine function and another input is e to the minus kt. So output will be what? Output will be a damping function, damp sine wave. Okay.
Okay. Okay, sir. And the causality you were telling, that is the
causality means output will be zero when t is negative. Okay, so it will be starting from 0. in all real life problem, everything starts from zero. We don't
Yes.
have a negative time.
Hmm.
Okay. So to make a system causal, we multiply by UT. Why we multiply by UT? Because UT starts from zero.
It starts from 0. Yes.
Yeah. So that means, let's say sine function. You don't know
Yes,
from
yes.
where it starts, but when a
Yes.
sine function is multiplied by UT, what happens? The sine function exact
Will be
starts
starting from
from
0.
zero.
So always when the function, when we'll be dealing with in discrete circuits, we really we are always multiplied by UT when the any kind of in discrete domain, when we are dealing with some signal to conform it with the time or causality, really in practical circuits, always we use it or multiply it with UT.
Look,
Difficult. No, no,
to make,
I'm asking that. It is my question, not like. Uh,
to make the thing simpler, let's see, any function, if it is
uh,
multiplied by UT, the function will become causal. That means it starts from zero. Okay.
During the time of measurement or data
Look,
acquiring, yes,
this,
we have to. Yes, we have to do that. That I am asking.
yes. So UT, so that means, UT or exponential function or del t, all of them, they have their relevance. Because using del t, we can make UT, or if we want to, let's say an application, I'm telling you, what is the application of del t? Say we have a continuous signal. We want to sample it. Sample it means what? Sampling
Sampling at a
continuous to
particular
get the,
time, and
means
that is
a regular
yes.
interval, we want to get the value.
So
Okay.
always at sampling, we have to multiply it always at delta square.
That means xt
That means an
into
impulse
del
circuit.
t minus k. If we do that, then what will happen? At k equal to 0, 1, 2, 3, in that way,
Yes,
we'll be
yes.
getting the sample. And the sample value is basically, again, this is analog, or this is, so we call it discrete analog, basically. So at discrete time, we are getting the value. Okay. So this is convolutions, basically shifting and multiplications. Okay. So these are the properties and all. All these things we will be getting in the book, should I discuss in details about the properties of convolutions and all? Or I can skip? Hello?
Yes, sir. Convolution you can describe because it is a very important and in most
Okay,
cases.
fine. Okay. Convolutions, you can think like that. What is a convolution? Now, yn, the convolution of x and hn, that is yn equal to x k into hn minus k, or it could be xn into h minus k. So it is basically shifting and multiplications. If you write xn minus k into hk, what is hk? Hk are impulse responses. What is impulse response? If you apply and impulse at the input, whatever you will get at the output is called impulse response. So a system's behavior is determined by the impulse response. That means for an impulse, how it is behaving. Any signal can be viewed as a sequence of the impulses, of course, of different values. For example, xn. Xn is what? If we take xn will have at n equal to 0 a particular value, n equal to 1 a particular value. So all these values are basically impulse, but not unit, this value. So hn indicates if an unit impulse is given, then what will get at the output. So that means when an xn will be given, then what should be the output? That is called the convolutions. So these properties are, if hn is shifted, if input is shifted, then output will also be shifted. Okay. So these convolution properties. Here also, in fact, if there two systems are connected in cascade, then convolutions will be h1n plus h2n. Then here also h1n plus h2n. So, now here, mathematically, hello, some noise is coming. Mathematically, it's very interesting. Xn and yn, h1n plus h2n. Now, what is h1n plus h2n? That means two systems.
Please, all of you, mute yourself.
Yeah. So H1n plus H2n. Now here, from the implementation point of view, we the engineers, we don't see only the mathematics. These are mathematics. But ultimately, at the end of the day, what we have to do, if it is a system, if the system has to be designed, then we have to consider this input is coming and output is available here, and this is implemented by a digital systems. Now, definitely to implement it, to execute these things will take some time. But if we divide, if we break it into two subsystems like H1 and H2n, ultimately they are added. But then H1n and H2n parallelly, they can do their execution. Let's say this is a fourth order systems. So when we'll be doing it, the systems, order of the systems will be lower. So computation time will be less. So this is advantage of the parallel system. So if a subsystem can be divided into subsystems which can be done parallelly, then the overall time will be reduced. So the properties of the LSI means linear shift invariant systems. LTI, in fact, in time domain, we call it linear time invariant. And here we call linear shift invariant because time is not here, time is replaced by n. Okay, so one is the causality, which is very important. Hn will be 0 for all n less than 0. Okay, so impulse response, Hn is the impulse response. So there is no impulse response before that. So, and for stability, Hk should be less than infinity. And some application. Now, before that, so for basic building blocks, forget about digital filter at this moment. So for making any systems, we need adder, multiplier, then some delay, and these are some pickup node, like xn from a particular point, a number of outputs can be taken. So basically, mathematical model for filter is hk into xn minus k, yn equal to hk into xn. Now, if you look at it, it's basically a convolutions. Yn equal to hk into xn minus k is basically the convolutions. So a system, what output it will be giving is purely determined by hk, impulse responses. That's why we call impulse response basically determine the behavior of the systems. And hn minus k is basically the delayed versions of x for k equal to 0 to n. And capital N is known as the order of the systems. In fact, the systems filter, we use it, the term are interchangeable. So interpretation, when input sequence passes through LTI systems, here in fact we will not call LTI, since it's a discrete system, we'll call it LSI system, linear shift invariant systems. So xn is the weighted by coefficients of the sample, and xn is delayed by the delay of the, so this xn minus k is, this indicates the delayed versions of xn. When k equal to 0, we get xn. K equal to 1, xn minus 1 means unit delay, 2 delay in that way. And hk's are the impulse responses. So here, let's see an accumulator. We want to design an accumulator. Accumulator does what? It adds it and accumulates. So this system should have memory. Why memory? Because the previous values are also important. Like Professor Datto, he was talking about these adaptive systems. No, for that, the memory has to be, is required very much. Here also, accumulator is accumulating the data, the previous data or previous sample values and getting stored. So that means we can write first the mathematics yn equal to summation of xk for k equal to minus infinity to n. Now, in reality, this will be k equal to 0 to n. Okay, so xk means what? Let's say y0. First, zeroth sample has come, x0. So y0 will be x0. Then let's say another sample, x1 has come. So y1 will be x0 plus x1. Then x0 plus x1 in that way. So we can write that yn equal to yn minus 1 plus xn. That means yn equal to present value and all the past values, whatever has been added. So recursively, it is represented as yn equal to yn minus 1 plus xn. Look, if we don't use this recursive expression, then we have to write yn equal to x0 plus x1 plus x2 plus x3. So as n will be increased, so many addition has to be done. Instead of that, what you are doing addition. Each time whatever it is added, it is getting stored. So when we are saying yn equal to yn minus xn, and if we make the model, then what? We need one adder. So input of the adders will be xn plus yn minus 1. So this is a delay, and typically we represent delay as z to the power minus 1. So here yn is the input to this delay functions. Output will be yn minus 1. So when yn minus 1 and xn is added together, we are getting yn. So just imagine, in a recursive way, very easily this is implemented. Otherwise, so many adders would have been required. So this is the example of an accumulator. Now, these accumulator concepts are very important in digital signal processing. We call it MAC unit, multiply and addition. There also the accumulator will be required. So here Hn is summation of del k. And here mathematical model of IR. IR is the difference between IR and FIR. If you see the FIR model, finite impulse response. Now, why we are calling it finite impulse response? Here, impulse response is finite. Like, when an impulse is given, then output will be, let's say, some values. After that, it will be 0. So response is finite. And here, if you see the expression, there is no past value. Yn doesn't depend on the past values of yn. It only depends on present value of xn and also the past value of xn. But it doesn't depend on the past value of yn. Whereas here, if you see that yn is dk yn minus k plus summation of pk xn minus k. So it depends on the present value of xn, past value of xn, and past value of yns. That's why it is called recursive functions. In a recursive way, like using the past value.
Excuse me, sir. Why it is called FIR and why it is IIR, that name?
Yeah, FIR is for finite impulse response filter. Why we are calling it finite impulse? Like here, if you give, instead of xn, if you give del n, output will be hn. That is the impulse response. So impulse response is finite. Okay. Impulse response is finite means what? You assume that at t equal to 0, some del 0 is applied, del n is applied. So output will be, let's say 1, then 0.5 or 0.25, then it will be 0. You just take an analogy. Let's say you have some toy, and using just impulse, you press it. Once you press it, you'll find tick, 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 and after that it is 0. You can think in that way. So impulse, you are applying an impulse at the input, and you are getting some output, and after some time it will be 0. So it is a finite impulse response. Now, why I'm calling it finite? You take this example. Here, Hn, let's say, when you are adding it, yn equal to yn minus plus xn. Now you tell me, this function is recursive or non-recursive? First, what kind of function it is?
Recursive.
Recursive, because output is a function of the past output. Now let's say, if I say that yn is hn, then xn will be del n. That is the impulse response. So what will be the hn? Hn will be del n minus 1 plus del n.
Yes.
Now again, del n minus 1 will be what? Del n minus 1 you have to represent in terms of that. Like hn minus 1 will be represented in terms of del n minus 1.
Yes.
So where it will be ended? You take this example, yn equal to, instead of y, you write hn. Then xn will be del n. So
Yes.
hn is y. hn equal to hn minus 1 plus del n. Now again,
Yes.
hn minus 1 will be what? In terms of again previous values? Again previous
So,
values. So
okay.
where it
So
will go?
it takes from 1 equal to 1, and so that it will take that n minus 1 means 0.
So it will go up to infinity, isn't it?
Yes. From where? That will be from 0.
Wherever you start, let's say n equal to 0, from 0 you start.
Yes.
So keep on going on.
Yes.
So
So the right hand side it will be continuing to infinity, but the left hand side should be starting from 0.
yeah,
Okay.
left hand side, you even there are two things. One is from the mathematical point of view. Second one is when you are thinking from the practical engineering point of view. Let's say from practical point of view, everything will be starting from 0, let's say. So for an impulse response, what is the definition of impulse response? If input is del n, then output will be hn. For any system, we consider input as xn and output is yn. So when xn is del n, then whatever we are getting at the output, that will be called hn. That is called impulse response. Response of the system due to impulse. So here in this expression, yn equal to yn minus 1 plus xn. So let's say xn equal to del n. Then yn will be hn. So I can say hn equal to hn minus 1 plus del n. Okay.
Yes, that I am telling.
Then
When
hn
it is
minus 1 will be again
yes,
hn minus 2 plus del n minus 1 in that way. So it will keep
Yes.
on going up to infinity.
Okay. Now my question is that when we are starting and practical circuits, the recurrence relation is actually we have to start from n equal to 0.
That is very simple. N equal to 0, I told at the beginning.
No, n equal to 0 will not help because n equal to 0 means a delta n minus 1 is not available.
For one first value, this is.
So your first value will be 1.
Yeah,
always 1.
That will
yes,
be,
yes.
that is the initial condition. So you call
that I am telling.
Given that this will
yes.
be 0. Okay.
Oh, okay.
And another thing, to make anything starting from 0, you just multiply that function with ut or un. In the continuous domain, you multiply with ut, and in the discrete domain, you will be multiplying with un. So
at n is equal to 0, xn will be delta 0. I mean,
exactly.
Yes. That will be assumption. After that, the recurrence relation will be continuing.
That's why xn term is there.
That's right. Is okay. So that means here now, if I analyze these systems, yn equal to yn minus 1 plus xn, that means output is a function of present input and past output. That's why it is recursive. And that's why it is infinite impulse response. So infinite impulse response and recursive, they are synonyms. They go together. Basically same. Okay.
Yes.
So here, if we see this model, this is what? This is recursive. That means that's why we call it IIR filter. That means infinite impulse response filter. So Y is a function of present input, past input, and past output. Okay. And another thing, both of them, FIR and IIR, both of them have memory. Why? Otherwise, if the memory is not there, then how you can compute the Y? Because the past value of xns are also required. So
both depends on past value of xn.
Exactly. So how the past value of xns are remembered? Can you tell that?
It should be like
who is working as a memory?
Feed forward.
No, feed forward. But which device is remembering?
Memory.
No, but memory is what here? I've not talked about memory here. But which device is working as a memory? Is the delay
capacitor?
Delay is a delay device. Is a delay
integrator.
So delay is acting as a memory. So xn minus k. Here yn equal to hk into xn minus k means what? h0 into xn plus h1 into xn minus 1 plus h2 into xn minus 3. So xn minus 3 is basically a delayed versions of xn. So if input is xn and there is a delay, what will be output?
So that means in terms of block, you are giving the conception. That
In fact,
is,
that
yes, sir.
look,
Yes, yes.
here, just have a look at it. So that's why the systems, to make this, we need an adder, multiplier, and delay. Okay. So here, for a delay, if xn is the input, then yn will be xn minus 1. So unit delay will give you xn minus 1 at the output. Okay. So these are the most important things. So FIR filters, here the impulse response is finite. In these expressions, if yn is hn, then x is the del. So this will become yn equal to hn will become this in this way, and you will get the finite impulse. But here you will get the infinite impulse response. That's why it's called IIR. So these are so can I go ahead with the next one?
Yes, sir.
So up to that, what conclusion we can draw? That in time domain we can see some hidden information which can be made available in frequency domain. So in fact, real life signals are basically available in time domain. Therefore, for spectral analysis, if we want to analyze these signals further, we want to mine some more informations from there, we have to go to the frequency domain. Okay. So next we will go to the frequency domain. So for continuous time domain, continuous time signals, Laplace transforms are used to convert the time domain to frequency domain for analyzing the signals. But for discrete domain, we use we convert these Z transforms we use for converting the signal to Z domain. Okay, so we must have to remember that Z transform is basically a discrete version of Laplace transforms. So now we'll go for the frequency.
Excuse me,
domain
sir.
analysis.
Sorry for interruption. We have 10 minutes left for this session. It will be ended by 10:45.
Only 10 minutes. So okay.
Yes, yes, yes.
Okay. Oh, by 10 minutes, whatever we can do.
Yes,
Otherwise,
sir.
we can
Yes,
do the
sir.
next day.
Okay.
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 Okay. In fact, it's good that some interactive session is going on. You were asking. So Fourier transforms is a mathematical technique that transforms a function xt to a function of frequency domain we call capital X omega. It is very closely related to Fourier series. So first we have to understand what's a Fourier series. Now Fourier series is there are many things in the slide, but if we talk in a simpler versions, periodic signals. First, Fourier series decomposes the periodic signal into infinite number of sine and cosine functions. But there must be some condition. If a signal is periodic and follows some condition which is known as Dirichlet's conditions, then that periodic function can be decomposed into infinite number of sine and cosine functions. So first, the periodic signal. What do you mean by periodic signal? If a signal xt, of course, now we are talking about continuous domain. Okay, xt is equal to xt plus capital T, where capital T is the period. Then the signal is said to be periodic because it repeats after a time period, capital T. So, what should be the conditions? There are three conditions. Xt is absolutely integrable. That means xt dt should be less than infinity. Or more precisely, you can say that xt dt should be finite. Then, in a finite time interval, xt has a finite number of maxima and minima. And condition 3, in a finite time interval, xt has only finite number of discontinuities. It's very important, the continuity and discontinuity. Just I'll give you an example. Now, there are 4 waveforms here. Now, first one is the sine, then the square, then the triangle, and then the sawtooth. Now, what is the basic difference between sine and square? Can you tell that? What is your observation? Of course, like this is sine function, this is square. That we understand. Other than that, from the continuous point of view, what is the difference between sine and square? the square function, is it a continuous function or discontinuous? Hello?
It's continuous function, but the thing is,
At the edge, at the edge.
at the edge,
No,
it is
is
at the edge
in
now.
fact, sine
In fact-
function is a continuous function forever.
Huh.
But here, square wave function, these
There
are
is
not
a discontinuity in the
These are-
sense and the bounded.
These are discontinuous. In fact. Even though
Right.
periodic,
At the
all
edge.
they are
Periodic,
periodic,
but discontinuous. Yes.
but it is a discontinuous. For an example, let's say when all of a sudden it's coming from high to low.
Yes, high to low.
At that point, it is discontinuous. Same is the case for your triangular waveform. It is going down, and from that point again is going up. So here, in fact, the signal. That's why.
So triangular is continuous, but square I can say is discontinuous.
Words, none of them are
No,
continuous.
none of this is not.
None of them
Because
are
at the point of inflection, before that, it is the gradient, and after that,
Exactly.
the gradient is different.
Yeah, this is only sine function is here continuous, but all of them are discontinuous. But Dirichlet condition says, even if it is a discontinuous, doesn't matter. But again, the finite within a period. So that means this square wave, triangle, sawtooth, all of them, in fact, they are, even though they are discontinuous, but finite number of discontinuities there within a period. For example, for a square wave, how many discontinuities there within a period?
So 1, 2, 3, 3.
Why 3? 2.
2,
Two.
right.
For
There
a
are two.
particular period. Two.
Okay, that means it is finite. So Dirichlet condition, we have to understand, it has 3 conditions. Number 1 is absolutely integrable over one period. Means what? XTDT. That means area within the period should be finite. XTDT is what? XTDT is nothing but area.
Area.
That should be finite within the period. Area should be finite.
Right.
Number 2 condition is what? In a finite number of interval, finite number of maxima and minima. Let's say here, how many maxima and how many minima are there?
Hello, hello.
How many maxima and how many minima are there?
For square wave.
For square,
ঠিক আছে 15টা না
one
11টা
maxima, one minima.
1 maximum, 1 minimum.
হ্যাঁ সেটা আমরা স্যারকে বলে দিয়েছি হ্যাঁ স্যার ওকে
Okay. Then, so finite number of maxima, minima, and finite number of discontinuity. So if these 3 conditions are satisfied, then the periodic signal can be decomposed into infinite number of sine and cosine. That's why GT, if GT is a periodic function, that means it repeats after a period capital T, then GT equal to A0 plus n cos omega nt, m equal to 1 to infinity, plus n equal to 1 infinity, bn sine of twice pi nt. In fact, here n and m, they can be same. The reason being, in fact, these are the frequencies of the signal, and this is called the fundamental frequency. So we can write, typically you can write am cos of n omega t and bn sine of this. Okay, so this omega 0 is called the fundamental frequency, and is the harmonics omega 0, omega 2, omega 0, 3, omega 0, and so on. And here, in fact, one thing, a0 has been taken out of this summation. Let's say omega a0 is not there, so the limit of this summation will be m equal to 0 to infinity. Here also 0 to infinity. Now cos 0 is what? Cos 0 is 1. So that's why it has been kept out of it. And sine 0 is 0. That's why the limit is 1 to infinity for both the cases. And this A0 is called the DC component. Okay. So that means the GT equal to A0 plus n cos of omega 0 nt plus bn sine of omega 0 nt for n equal to. So periodic signal, that means we can say that within this square wave or triangular wave or sawtooth wave, there are infinite number of sine and cosine components are there. Even if you take the full wave rectifications. Now from the full wave rectifier, if you take this Fourier series, then what you will get? You will get a DC component plus all this, and by filtering, you take the DC out, and that is the concept of our, in fact, AC to DC conversions using this.
Sir?
But here, hello.
Sir. This is Sabyasachi. বলছি যে triangular wave, why can't I say triangular wave as continuous?
Now triangular is
No,
continuous, I think, sir.
Because left hand
Triangular
limit,
is
left
there
hand
a left
limit
hand limit.
No,
and-
it is not continuous.
at this points, at
It
the
is
peak.
not continuous. Again, I am telling you, it is not continuous.
Ah.
Why? It should have gone down. Why at this point again it is going? Is it following that? Continuity means this is triangular wave. Let's
No,
consider
no, sir.
this.
Continuity
Sir,
means
continuity is
the left hand and left hand limit,
Limit
and the right hand limit.
and limit will be
And
equal to
the-
functional value.
Yes. That should
No,
be
left hand
in
limit.
the
Look,
triangular.
again I am telling you.
But ramp is not continuous. Ramp is not continuous. sir,
Ramp
কিন্তু-
square,
No,
square.
not only RAM.
Ramp and square.
This
Sawtooth and
function
square.
is not continuous. I'm telling you again. This is not continuous. Otherwise, it would have gone down totally. Please try to concept in that way.
Okay.
Otherwise, it would have gone down totally. At this point, you take this triangular waveform. Okay, in the
Right.
second box, you take the point from where it was going down.
Right.
Why it is going up? None of them are continuous. All of them are discontinuous at this particular point. Okay, at this point, let's say triangular waveform. Take the second box.
Hello, excuse me,
Second
sir.
box. Hello.
Sir, we are running out of time, sir.
Okay.
Yes, sir. Now we have to.
So in fact, anyway, we are stopping now.
Sorry,
But
sir,
one
we
thing
are running
again, I'm
out of
telling
time,
you.
sir.
Yeah,
Yes.
just 1 second. Square wave, triangular, sawtooth, all of them are basically, in fact, the discontinuous. At that point. So
Right.
the number of discontinuity is 2.
Right.
Okay.
Yeah.
Okay, Madhumita, what?
Yes, thank you,
and
sir.
Subhashaji can
Sir,
copy now.
sir,
Can-
thank you for giving your nice lecture
Nice
and elaborating
simple
and